My name is Anya Katsevich, and today I'll be talking about statistical inference for high variance Gaussian mixture models. A Gaussian mixture model is a model for data which come from several distinct subpopulations, each of which is normally distributed. This figure shows two GMMs, both of which are a mixture of three subpopulations. The blue, green, and purple points at the bottom represent samples drawn from the mixture, and the functions are the probability densities corresponding to the mixtures. Note that the peaks of the density on the left are more clearly separated than the peaks of the density on the right. And similarly, the different colored points are more clearly separated into subgroups for the mixture on the left than the one on the right. This is because the standard deviation sigma of each of the individual subpopulations is smaller for the mixture on the left. And we'll be interested in mixtures like the one on the right, where it's more difficult to distinguish the subgroups from one another just by looking at the data. The problem I'm going to talk about is how to estimate these subpopulation means theta 1 star, theta 2 star, and theta 3 star based on independent observations drawn from the mixture. One application in which data are naturally modeled as a noisy GMM is imaging data from cryo-electron microscopy, or cryo-EM. In cryo-EM, many copies of a molecule are frozen in a sheet of ice. The molecules are frozen in different orientations, which are unknown to us. We then observe images of these molecules, which tend to be very noisy. And the goal is to recover the clean image of the molecule in any one of the orientations. We can think of the clean images of the rotated molecules as our center theta star, and the noisy versions of the images as the data yi. If we knew which orientation each image corresponded to, we could sort them by orientation, and then to get an estimate of the clean image, we would simply average all of the images corresponding to each of the different orientations. So for example, here we would take all of the images with the purple border and average them to get an estimate of the clean image with the purple border. But the problem is that we don't know which orientation each image corresponds to. So this straightforward method of recovering the clean images is not available to us. And this conundrum is common to all Gaussian mixture models. We don't know which group each data point belongs to, and this makes parameter estimation difficult. So to summarize, assume we are given samples y1 to yn drawn from a mixture of three Gaussians with means theta 1, 2, and 3 star, and variance sigma squared, which we assume is very large and known to us. The goal is to estimate the means theta star. This is a simplified setting to make the concepts I'll talk about more transparent. In the general setting I studied, there can be an arbitrary number of subpopulations and the data can have any dimension. But it is important that all the subpopulations have the same variance sigma squared and that it's large. There are several approaches to parameter estimation for Gaussian mixture models. Probably the most widely used is expectation maximization, or EM. And there have been many variations of the algorithm that have been developed. The second approach is called method of moments, or MOM, and it has been primarily used for mixtures in which there are additional constraints on the mixture centers. So this was the case for the cryo-EM data, for which we knew that the mixture centers are rotations of each other. For GMMs with additional constraints, it's been observed that EM and MOM perform similarly when sigma is large. It turns out that the error in the estimator produced by either method is proportional to sigma to the k for some k greater than 1. If we had a single population, then a good estimate for theta star would be the sample mean when that has error proportional to sigma. So the fact that the error is larger than sigma is indicative of the fact that we can't reliably separate the samples into their respective subgroups. And the rest of the talk, I'm going to explain this connection between the two methods for general GMMs. But first, let me go over the two algorithms, starting with EM. So EM is an iterative procedure similar to k-means clustering. We start with an initial guess for the locations of the three centers. And based on this estimate, we compute probabilities Pij that sample Yi came from group J for each of the n samples and each of the three groups. And then using these probabilities as weights, we form three weighted averages, which are our new estimates of the means theta. And then we iterate this procedure with a new estimate of theta until convergence. So let's look at the two steps in more detail. In the first step, we compute these probabilities Pij based on the distance between the sample Yi and our current estimate of the J center of theta J. And the larger this distance, the smaller the probability that Yi came from group J. In the second step, we combine the samples using the Pij as weights. The idea is that if Yi is far from theta J, then the contribution of Yi to the new estimate of theta J is small. So for example, in this diagram, this purple point on the far right will contribute very little to the new estimate of theta 1. It turns out that at each iteration of EM, the negative log likelihood decreases. The log likelihood is a function of the parameters theta. For a fixed theta, it's given as the log of the probability of observing the data points, given that the data was drawn from a mixture with centers, theta 1, theta 2, and theta 3. And it turns out that the minimum of the log likelihood over all possible parameters is attained at the true theta, which is theta star. So the fact that the log likelihood is decreasing at each iteration of EM suggests that the theta k could be converging to the true parameter theta star. But this isn't actually guaranteed, and convergence of EMs depends on whether the function minus LL has local minima. Okay, so now let's talk about the method of moments. We define the pth moment of theta star as the average of the theta j star raised to the pth power. So for example, the first moment is the average of the three centers, and the second moment is the average of the squares of the three centers. These moments, MP star, are unknown, but we can estimate them from the data. So the first step in the method of moments is to compute estimates MP hat of MP star from the data for p equals 1, 2, and 3. And then we solve for estimates theta 1 hat, theta 2 hat, and theta 3 hat of the true centers based on our estimates M1 hat, M2 hat, and M3 hat. So let's look at how these two steps work. First, consider estimating the first moment, which is the average of the theta j star. Remember that we don't know which of the groups each sample comes from. But we don't actually need this to estimate the average of the theta j star. We can actually just average all of the samples. And since we know that approximately a third of them come from each group, the average over all of the samples breaks down into an average of the averages over the individual groups. And a similar estimate gives us the second moment, but the only difference is that this time we need to subtract out the variance sigma squared. So for the second step, we solve this system of polynomial equations. And the solutions are estimator of theta 1 hat, theta 2 hat, theta 3 hat. And I'll just note that for the general setting, the method of moments works the same way, but the second step becomes much more difficult. For example, in higher dimensions, this first equation is a vector equality, the second equation is a matrix equality, and the third equation is a tensor equality. Okay, so now let's talk about the connection between the two methods. First, let's define this function MP of theta as the average of the coordinates of theta to the pth power. So for example, MP of theta star is just the same as MP star, which we defined before. And our result assumes that we have access to an infinite number of samples. The gist of the result is that when sigma is large, we can write the negative log likelihood as a linear combination of the squared difference between MP theta and MP star. And these square differences are weighted by sigma to the minus 2p, which gets smaller as p increases. As a result, the iterations of EM match the moments of the parameter theta to the true moments, one by one, starting from the first moment. And we actually initially proved this result for a subclass of GMMs, but then a paper came out first which had the same result. But thankfully, we figured out how to generalize it to a much bigger class of GMMs. To go into a bit more detail, we can break down the result into stages. In the first stage, we show that minus LL can be written as a constant plus 1 over 2 sigma squared times the difference between the first moment squared, plus another term whose magnitude is order sigma to the minus 4. So suppose we use some iterative procedure to minimize minus LL, such as EM. Since the sigma to the minus 4 term is much smaller, the procedure will effectively ignore it and first try to minimize this difference of squares. So as a result, by the end, we'll have a theta whose first moment is given by M1 star. So this is the end of the first stage. In the second stage, we assume that we now have that M1 of theta is given by M1 star. For such theta, we can write minus LL as a constant plus 1 over 4 sigma to the fourth times the difference between the second moment squared plus another term of order sigma to the minus 6. And so now the iterative optimization scheme will proceed as before and will ignore this lower order sigma to the minus 6 term. And so it'll try to minimize this difference. This is squared difference, but it will stay on the subset of thetas for which the first moment is given by M1 star. So at the end of the second stage, both the first and second moments of theta will match the true first and second moments. And in this third stage, we have a similar expansion of minus LL, and so on for higher order moments. So in general, in the pth stage, we assume that the first p minus 1 moments match the true p minus 1 moments, and we can write minus LL in terms of the square difference of pth order moments. So this figure demonstrates the distinct minimization stages of EM. The blue points depict the EM trajectory based on 1 million observations of a mixture with sigma equals 4. So this red plane is the set of points theta such that M1 of theta is equal to M1 star. And it actually only takes one iteration of EM for the first moment to match the true first moment, which is why all of the blue points we see here already lie in the red plane. So starting from the second iteration, the EM updates are approaching the black curve, which is the set of points where the first 2 moments match the true first 2 moments. Once the points reach the black curve, they move along it towards the true theta star, and as a result, the first 3 moments of the estimate will match the true 3 moments. So this plot shows the second and third moments of the kth iterative theta k approaching the true second and third moments as k increases. And note that M3 actually does not monotonically converge to M3 star. It only truly begins to converge once M2 of theta k has already been matched to M2 star. So the connection between EM and MOM has several consequences. First, it gives us a tool to analyze the performance of EM. Even though EM is in widespread use, There are a few settings in which the algorithm provably converges to the correct set of parameters theta star. Due to the connection with moment matching, we now know that when the noise is large, we can determine whether EM converges based on whether we can pass through each moment matching stage without getting stuck in a local minimum. The connection between the two methods also implies that the error in the EM and MOM estimators should have the same dependence on sigma. The error in the MOM estimator is the same as the error in the estimate of the highest order moment. And in our 3-component mixture example, we use 3 moments, and the error in the third moment can be shown to be proportional to sigma cubed over square root of n. And although MOM and EM have the same error, MOM is actually more efficient than EM. For MOM, we only use the data once to estimate the moments. But in EM, we need to pass through the data at each iteration. And since the number of samples needed to get an accurate estimate scales like sigma to the 2k, EM can be prohibitively expensive. So our results suggest that MOM may be preferable to EM in the case of high noise. It is possible, though, to speed up EM by parallelizing it. Each iteration requires n independent computations and 1 summation of n terms. And to check our theoretical result about the log likelihood, when sigma is very large, we implemented a parallel version of EM. And the simulations confirm that the EM trajectory matches the moments of the parameter estimate theta k to the true moments 1 by 1. So these are the references I cited. And to conclude, I'd like to thank my advisors, Afonso Bandera and Jonathan Weir, and of course, the generous support of the CSGF these past 4 years. Thank you.